We're going to start this deep dive with a little bit of a cosmic visualization. So I want you to step outside, metaphorical telescope in hand, and just look up.
Okay, I'm with you.
You are looking for an event that signifies the absolute end of matter. I mean, the most powerful, the most energetic explosion the universe can possibly stage.
You are describing pretty much perfectly a gamma ray burst, a GRB.
Exactly.
These are the fireworks of destruction. They usually mark the final collapse of a really massive star or, the merger of two super dense objects like neutron stars.
And crucially, they are fleeting. That's the key word here. They are the ultimate cosmic strobe light.
Blink and you miss it.
Totally. They're supposed to be over in an instant.
Ah.
A short GRB, we're talking milliseconds. Even what astronomers call a long GRB is typically over in what, under 2 minutes?
Yeah, under 2 minutes is standard. If you get a really, really extended one, you might be looking at maybe an hour or two max.
They are cosmic snaps of the fingers.
They have to be. It's a signature of physics working incredibly fast.
Yeah.
The energy source is consumed, the light dies. End of story.
Except, on July 2, 2025, Earth's high-energy sensors didn't pick up a snap of the fingers. They picked up an endless, terrifying roar.
And that is the beginning of our deep dive into GRB 250702B.
This explosion, which was picked up by this whole network of astronomical sentinels we have watching the sky, it didn't just break the rules.
No, it shredded them. It took the rule book and just lit it on fire. This event, registered a gamma ray duration that lasted for at least 7 hours.
7 hours.
Let that sink in. The clock time was around 25,000 seconds of continuous detectable gamma ray activity.
Okay, so you said the old record was maybe a couple of hours, in an extreme case. 7 hours is.
Yeah.
That's nearly doubling the previous record holder for the longest burst we have ever cataloged.
It's in a completely new category.
And what's truly stunning is when you start to look at the cumulative destructive scale. The energy release here was calculated to be so extreme.
Yeah.
Get this. It was equivalent to the entire energy output of 1,000 suns.
1,000 suns.
Shining for 10 billion years.
Wait, for their entire lifetime?
For their entire 10 billion year lifetime. And all of that energy was condensed into just a few days of activity, all coming from a single distant point in the sky.
It is genuinely difficult to wrap your mind around that kind of power. It's just a number at that point.
It is.
And for us, the time perspective is essential here. The light from this catastrophic event.
Yeah.
It traveled for 8 billion years to finally reach our detectors.
8 billion years.
So when this black hole was consuming its companion star and launching this monstrous jet of energy, our sun, our entire solar system, hadn't even started to form yet.
It wasn't even a cloud of dust.
Not even a twinkle in the universe's eye. We are witnessing an ancient violent death that directly challenges everything we thought was possible in, how stars die.
And the mystery only multiplies when you actually look at the graph of this event. It wasn't this smooth decline, like a dying ember. The sources describe it as repeating.
That's the part that really gets me.
It was triggering the high-energy monitors, not once, but multiple times, over the course of a day.
So it's like a flare, then it dies down, then another flare.
Exactly. It was as if the universe was just refusing to let this event fade. It was hitting the restart button on a catastrophe over and over and over again.
This initial data, it must have forced an unprecedented response. Researchers would have immediately realized that no single instrument they had was designed to handle this.
How so?
Well, you design satellites like Fermi or Wind to capture a short, massive pulse of energy, you catalog it, and then you move on to the next one.
You're not expecting one to just stay on for your entire shift.
Exactly. GRB 250702B demanded a complete shift in strategy. It became a global, multi-day surveillance operation that had to span the entire electromagnetic spectrum, from visible light all the way up to the highest energy gamma rays.
The universe had served up an impossible object.
And solving it was going to require a coalition of telescopes.
Okay, so let's unpack this problem. GRB 250702B lands on the desks of astrophysicists around the world, and it immediately presents what seems like a physical impossibility.
It really does. It's a conflict between two fundamental constraints of, how stars are supposed to die.
That's the ultimate physics paradox.
Right. So when we categorize GRBs, we rely on these established rules. We have short GRBs, which are pretty straightforward. They come from the rapid, sort of clean merger of two compact objects, like two neutron stars slamming into each other.
Quick, violent, and over.
And then we have the long GOBs, which is what we're focused on here. Those come from a collapsar.
Which is the collapse of a really, really massive, rapidly spinning star into a brand new black hole.
Exactly. And for a long GRB, the mechanism that launches those jets, the beams of gamma rays we see, is the accretion disk that forms around that newborn black hole.
So the black hole is basically eating the guts of the star that just died to create it.
That's a great way to put it. The central engine is the black hole rapidly consuming the star's core. But here's the critical limitation, the first big problem. That engine is fueled by the angular momentum.
The spin.
The spinning energy, that was contained within the original star's core. It's all about how fast that star was rotating right when it died.
And this is where we hit the first contradiction, the one the scientists called the long duration, or the fuel problem.
Precisely. All the theoretical models, based on the physics of a single collapsing star, they all suggest that the rotational energy available to feed that jet engine is severely limited.
There's only so much spin to go around.
Exactly. The longest theoretical lifetime for a standard collapsar engine is only a few thousand seconds.
Okay, so a few thousand seconds. That's maybe an hour, hour and a half at the absolute maximum of continuous activity.
Right. And then the available rotational energy is just gone. It's exhausted. And the jets have to shut down.
So trying to get 7 hours, let alone the days of flaring we saw, out of that, it's like trying to drive a car across the entire country using the energy stored in a single AA battery.
That's a perfect analogy. The fuel source is physically insufficient for the task. It just doesn't work.
The math is broken.
Completely.
Okay.
And that's the magnitude of the problem. I mean, if you need an engine to run for days, you would naturally assume you need a massive, slow-burning fuel source and a huge engine.
Like the supermassive black hole at the center of a galaxy, right? Something that's just enormous and can eat stars for breakfast.
That would be the logical assumption. But that's where the second contradiction just slams the door shut on that idea.
And this is the short variability, or the engine speed problem.
This is the data point that truly baffled everyone. It's just wild. If you look at the light curve of this GRB, you don't see those slow, massive waves of energy you'd expect from a giant engine.
Easy.
You see incredibly rapid, intense flickering. The observations reveal clear sub-second structure.
Meaning the light was fluctuating, getting brighter and dimmer in less than a second.
Yeah. The calculated rest frame minimum variability timescale, or MVT, was astoundingly short, about half a second. 0.5 seconds.
Okay, wait, let me make sure I'm following this, because the MVT, the flicker speed, that's the physical key here. The flicker speed tells us the size of the engine, right?
It does. It all comes down to the principle of causality. For an object to fluctuate in brightness, to flicker, the entire region that's emitting the light has to have time to communicate with itself.
And the fastest anything can communicate is the speed of light.
The universal speed limit.
Yeah.
Therefore, the time it takes for that accretion disk around the black hole to flicker can't be shorter than the time it takes light to cross the whole thing.
So if the flicker time is half a second, the engine itself must be small enough for light to cross it in less than half a second.
Exactly. This rapid sub-second flickering is the undeniable signature of an extremely compact, rapidly spinning central engine. There was no other conclusion. The team realized that the engine powering GRB 250702B had to be a stellar mass black hole.
Okay, hold the phone.
I know.
The universe has just delivered an explosion that lasts for days, which implies a massive, slow, gigantic engine.
Right.
But the actual flicker speed, the data, tells us the engine is tiny. A stellar mass black hole may be weighing only 3 times the mass of our sun, with an event horizon, what, about 11 miles across?
That's the size we're talking about, the size of a city.
So it is simultaneously the fastest engine and the one with the longest fuel supply ever witnessed. That is a truly impossible combination under any standard astrophysical model.
It's a paradox in every sense of the word. And if that wasn't enough to make their heads spin, they had to rule out the most obvious culprit for any kind of long-lived explosion.
The supermassive black hole. The big guy at the center of the galaxy that can sustain a jet for, like, millennia.
Had to be ruled out. And it came down to a simple matter of real estate. Location, location, location.
What do they find?
So when the Swift satellite and later the JWST pinpointed the source with incredible precision, they found the burst was located inside a distant, dusty, massive galaxy. But, crucially, the burst was highly offset. It was non-nuclear.
Meaning not in the center.
Not even close. It was about 5.7 kiloparsecs away from the galaxy's core. That's deep in the galactic suburbs, in a dark, star-forming dust lane.
So that geographical constraint immediately eliminated the host galaxy's supermassive black hole as the power source.
Yeah.
It's just in the wrong place.
Absolutely. So tiny, fast engine, way out in the galactic boonies, yet it burns for days. Where in the world did the fuel come from?
And that question becomes even more complicated thanks to the incredible precision of the Einstein probe.
Oh yeah, the EP. This is the precursor plot twist.
The EP is designed to monitor the X-ray sky, and it detected significant X-ray emission a full day, nearly 24 hours, before the main furious gamma-ray burst sequence even began.
A pre-show.
A pre-show. A warning shot before the main explosion.
Which suggests the black hole engine had already started up. It had quietly started accreting material and running long before the spectacular ultra-relativistic gamma-ray jet finally ignited and roared out for 7 hours.
Standard GRBs are instantaneous. A star collapses, boom, it's on. They don't give you a day's notice.
Never. The source material states it unequivocally. They say this mixture, the extreme duration, the high energy, the hard spectrum, and this incredibly fast sub-second variability is, and I quote, incompatible with all confirmed gamma-ray burst progenitors.
It demanded a new theory of cosmic violence.
Yeah.
This is that moment in the story, right, where the scale of the challenge forces the scientific community to become detectives and rally this unprecedented effort.
Exactly. If your conventional toolkit for explaining how stars die is completely useless, you have no choice. You have to build a new one using every single instrument you have available.
And it was a monumental collaborative effort. It really showcases the power of multi-messenger and multi-wavelength astronomy.
It really does. As the researchers themselves noted, because this burst was so incredibly long, no single high-energy monitor could capture the complete life story of the event.
It was just too much data for any one satellite.
Way too much. It required the combined coordinated power of multiple spacecraft and ground telescopes, all working together for days on end.
So let's detail this satellite coalition. Who were the key players? Who provided the pieces of evidence that built the case?
Okay, so we start at the top, with the core evidence in the highest energy bands. The initial detection, and crucially, the confirmation of that incredible duration came from the workhorses, Fermi GBM,
The gamma-ray burst monitor.
and CONUS Wind. Now, Fermi is interesting because it actually triggered multiple times as the event pulsed on and off, which is what first cemented that unusual repeating nature.
So it wasn't just one long scream, it was a series of screams.
That's a good way to put it. And what did they confirm about the energy level itself?
But they confirmed the duration, yes, but more importantly, they defined the burst as a hard spectrum event.
What does that mean in simple terms?
It means the light was incredibly high energy. They detected photons, particles of light, with energies reaching 5 to 6 mega-electron volts. MeV.
Okay, and why is that high energy level important for ruling things out?
Because it's a specific signature. That MeV level detection confirms it was a genuinely high-energy, non-thermal emission. It's characteristic of a classic GRB jet. It immediately ruled out a lot of other softer, more benign events.
Like a typical X-ray flare or some kind of exotic magnetar flare?
Exactly. Those things operate at much lower energy scales. With this data, we knew, without a doubt, we were dealing with an ultra-relativistic jet engine. The light was incredibly powerful and focused, like a laser beam, not just a gentle, widespread glow.
Okay, so that's the power and the duration lockdown. Now we move to the surveillance team, the ones tracking the lingering activity.
That's where SWIFT and NuSTAR were absolutely essential. SWIFT's X-ray telescope got the first precise location, which is what allowed everyone else to point their telescopes in the right direction.
The initial targeting system.
Exactly. But NuSTAR, the Nuclear Spectroscopic Telescope Array, provided the smoking gun for just how persistent this thing was.
It was watching the afterglow.
Right. NuSTAR tracked the extended activity and, crucially, it observed significant X-ray flares that were still happening up to 2 full days after the main 7-hour gamma-ray burst had seemingly subsided.
2 days later, and the black hole is still flickering and flaring.
It's still burping. That longevity proved that the black hole wasn't just, cooling down after a big meal. It was still actively accreting matter.
It just refused to shut off.
It refused to shut off, which implies some mechanism was still delivering fuel to the engine's inner disk days after the whole thing started.
Incredible. And finally, to really understand what kind of event this was, they had to understand where it happened. The distance.
And that's the distance team. The ground and orbital heavy artillery. You've got the Very Large Telescope, the VLT, Keck, Hubble, Gemini. But The single most critical piece of information, the redshift, came from the James Webb Space Telescope.
JWST, using its NIRSpec instrument, the near-infrared spectrograph.
So why did they need JWST for this? Couldn't Hubble see it?
The host galaxy, while it was massive, was absolutely drowning in dust. The sources note extreme host attenuation, which is just a fancy way of saying dust extinction.
So it was hiding behind a cosmic dust cloud.
A really, really thick one. The amount of dust was estimated at an AV of approximately 11 magnitudes. That's so high that the visible light was almost entirely blocked.
11 magnitudes of dust. That's like trying to read a newspaper through a thick woolen blanket.
It really is. Without JWST, the distance would have been pure speculation. But with its specialized near-infrared capabilities, it could just cut through that dust veil like a surgical laser.
And what did it find?
With that NIRSpec data, the team, led by a scientist named Benjamin Gompertz, they determined the exact redshift. Z is approximately 1.036.
And that number confirms the 8 billion year light travel time.
Yes, and that solidifies the immense true energy output of the burst. Now, they had all the pieces.
So with all that data collected, extreme duration, fast variability, non-nuclear location, hard spectrum, persistent activity for days, they could finally start ruling out the standard models.
Let's start with the big guys, tidal disruption events, or TDEs.
This is where a black hole shreds a passing star. And they initially looked promising, right?
Yeah.
Because they are known for long, drawn-out emissions. They fit the duration criteria.
They do, but they fail the speed test. Catastrophically.
How so?
A TDE is usually powered by a supermassive black hole. Even the fastest, most extreme TDE we've ever seen, an event called Swift J1644 plus 57, which was already considered ridiculously fast. Its minimum variability timescale was about 40 seconds.
40 seconds of flicker time for a huge engine.
Now, compare that 40 seconds to GRB 250702B's required half-second flicker time. The TDE engine is about 80 times too slow.
So for the analogy, if a TDE's variability is like the massive slow waves you see when a giant ship passes under a bridge, big slow changes.
Then GRB 250702B is the rapid sub-second beat of a hyper-fast video game button mash.
I love that. The immense size of a supermassive black hole just physically prohibits that kind of rapid fluctuation. The light travel time constraint makes it impossible.
So strike all supermassive black holes. They are too slow and too big to generate that half-second speed.
Okay, so now we turn to the second standard model, the collapsar, the collapsing massive star.
Collapsars fit the speed test beautifully. They create a stellar mass black hole about 11 miles wide, which can easily flicker at half a second. The engine size is perfect.
But they fail the duration test, the fuel problem.
Exactly. Or rather, the amount of available fuel is wrong. As we said, the fuel for a collapsar is the rotational energy of the star's core. That fuel is physically limited. It provides accretion time for only a few thousand seconds.
This one ran for.
The analysis indicated the central engine of GRB 250702B ran for up to 85,000 rest frame seconds.
The discrepancy is enormous. How do you possibly reconcile a tiny stellar mass engine with enough angular momentum to run for days?
You can't. Not if you only rely on the spin inside the star. The researchers were forced to conclude that the only viable solution was to tap into something else.
An external power source.
Exactly. They had to tap the orbital angular momentum, the spin and energy that's locked in the orbit of two objects, which only exists in a binary system.
The black hole had to be carrying its massive fuel source with it.
It's the difference between spinning a top with your finger, you give it one push and it runs out of power,
and connecting that top to an external, continuously unwinding drive belt. The initial spin doesn't matter anymore. You need continuous energy being added from an outside source.
That's a conceptual shift. They needed a mechanism that allowed a stellar mass black hole to continuously and violently acquire new, highly rotating material over a period of days.
It's the only way.
It is the only way to generate such immense yet sustained collimated power. And here's the kicker. The total energy, once they corrected for the jet's narrow angle, was actually pretty typical for a regular long GRB.
So the energy wasn't the outlier?
The duration of the energy release it wasn't about more power. It was about keeping the power on for an impossibly long time.
And this brings us to the dramatic reveal. The puzzle is solved by looking at the oldest ingredients in the cosmos, stars, and black holes, but just arranging them in a brand new way that creates this new, incredibly durable engine.
The only way to reconcile the extreme duration, the long fuel problem, with the fast engine, the stellar mass black hole, required invoking that orbital angular momentum.
Which means we are looking at a case of celestial cannibalism, a binary system where one object consumes the other.
And the gamma ray team, heavily influenced by scientists like Eliza Knights and Eric Burns, they landed on the Helium Merger Model as the strongest possible candidate.
Okay, so let's break that down.
This model proposes the merger of a stellar mass black hole, maybe around 3 solar masses, with a very specific type of companion star.
A stripped helium star.
A stripped helium star.
Okay, that sounds pretty theatrical. What is a stripped star?
It is, in a cosmic sense. So a normal star has this massive outer envelope made of hydrogen. A stripped star is one that has lost that entire envelope.
How does that happen?
Either through really strong stellar winds, or, more likely in this context, the gravitational stripping by its close binary companion, the black hole.
The black hole has been slowly stealing its atmosphere over millions of years.
Exactly. So what you have left is the dense, tightly packed helium core of the star. This core is smaller than our sun, but it still contains immense mass.
So we have a tiny, dense black hole orbiting a dense helium core. How does that turn into a 7-hour gamma ray burst?
The process is called the common envelope phase. It's wild. The black hole spirals inward, closer and closer, and eventually it becomes completely immersed within the dense envelope of that helium star.
So it plunges inside the star.
Yes, it begins consuming the stellar matter from within. It's a prolonged, violent act of cannibalism from the inside out.
Wow. The black hole essentially dives into the star, carrying its fuel source with it inside the star itself.
Exactly. And this plunging, high-speed interaction generates an accretion disk around the black hole. But the crucial part is that the material in that disk possesses enormous angular momentum, which it gets from the original tight orbit of the binary pair.
That's our unwinding drive belt.
That is the drive belt. It continuously feeds the stellar mass black hole highly rotating material, keeping that jet firing for the observed 7 hours, and the astonishing 85,000 rest frame seconds of activity.
So the black hole never runs out of fuel, because it's constantly getting new, high angular momentum material delivered right to its event horizon.
That's the only way to keep that tiny 11-mile-wide engine running for days on end.
It's the cleanest fit for the full spectrum of data we saw. It explains the fast flicker time, the long duration, and that hard, high-energy spectrum.
It checks all the boxes.
Now, you mentioned there were a couple of competing disruption models that tried to explain some of the other weird clues, like the precursor and the timing. We shouldn't ignore those.
No, those were tantalizing clues. One was the microtidal disruption event, or a TDE.
That one involves a stellar mass black hole stripping a standard main sequence star, like our sun.
Right. And this model was really attractive because it offered a natural explanation for that day-long separation between the X-ray precursor and the main flare.
How so?
That time difference could just be linked to the star's initial orbital period before it was destroyed. It made sense.
And then there was the even more exotic idea, the one involving an intermediate mass black hole.
Yes, the WD-IMBH TDE, a white dwarf star being disrupted by an intermediate mass black hole.
And this scenario gained traction because of a really compelling, even if it was inconclusive, piece of evidence.
The periodicity of the main burst, the rhythm.
Tell us about that rhythm.
The brightest gamma ray emission didn't just fire continuously, it occurred in these really strong pulses. And when they measured the time between those pulses, they found them to be near integer multiples of approximately 225 seconds.
Wait, so there's a pulse, then about 47 minutes pass, then another pulse, then maybe 94 minutes pass, then a third?
Something very much like that. It's suspiciously rhythmic for a cosmic explosion.
It absolutely suggests a periodic source, not just a random collapse.
It does. And if those flares represented the white dwarf making these repeated partial grazing passes close to the intermediate mass black hole before its final destruction, well, that model could potentially explain those repeating rhythmic bursts.
But despite that tantalizing periodicity clue favoring a disruption model, the team kept circling back to the helium merger.
They did.
Why did the final verdict still favor the helium merger model over the rhythmic disruption model? What was the tiebreaker?
In the end, it was the hard data from the high-energy satellites. The WD-IMBH model, the rhythmic one, struggles profoundly to explain the extremely hard spectrum and that maximum photon energy they detected up to 5-6 MeV.
It can't generate that much power.
That level of energy output is generally inconsistent with the softer spectrum you'd expect from a white dwarf disruption. The helium merger, while maybe not having a perfect explanation for the 28-25-second rhythm, remained the most robust and consistent fit for the full range of high-energy properties observed in GRB 250702B.
So it's the gold standard explanation for combining a fast engine with a day-long fuel supply.
Okay.
So GRB 250702B is so much more than just a record breaker. It's a paradigm shift.
It is.
It teaches us that the universe isn't limited to this simple collapsar versus merger dichotomy that we spent decades defining. There is this new pathway, celestial consumption, through a binary merger.
This is crucial, growing evidence for a brand new ultra-long class of GRB. It confirms that the merger of a compact object, in this case a black hole with a stripped star, is a viable pathway for generating one of these ultra-relativistic jets.
We'll have to update the textbook. And I find it fascinating that this cosmic light show is immediately linked to the future of multi-messenger astronomy. It's not just about the light we saw, but about the ripples it must have created in space-time.
That is the profound implication here. These tight binary systems, a black hole spiraling into a star, they have to be massive sources of gravitational waves.
Of course.
As the two objects orbit each other, they radiate energy away as gravitational waves, which is what causes the orbit to decay and leads to the merger we just observed in gamma rays.
So this firmly links the ultra-long GRB class to the field of gravitational wave astronomy.
Without a doubt, future observatories, things like LIGO, Virgo, CAGRA, they will potentially be able to detect the gravitational wave signal just before the gamma ray burst even ignites.
Which would be the ultimate astronomical surveillance system, knowing a star is about to be consumed before we see the flash. And from a cosmological perspective, these events can tell us a lot about the universe itself, can't they?
Absolutely. The Helium Merger Model predicts these events naturally arise in regions of active star formation.
Where lots of new stars are being born.
Right. Therefore, if we start cataloging more of these ultra-long GRBs, they become powerful tracers for mapping how star formation evolved across the entire universe, especially at these high redshifts we're observing here 8 billion years ago.
And the host galaxy of this event fits that profile perfectly.
Perfectly. It was massive, dusty, and highly asymmetric, all completely consistent with these actively star-forming, high-density regions we see in the early universe.
Okay, so we have to address the major missing piece of evidence, the one observational hurdle that remains in the model.
The missing stripped envelope supernova.
Right.
The Helium Merger Model makes a very specific prediction. When the black hole plunges into that star, the catastrophic consumption that follows should trigger the star itself to explode.
So you get the GRB jet, but you should also get a big, bright supernova explosion, a powerful optical afterglow that follows the GRB.
A clear, bright, messy cosmic aftermath.
And we didn't see one.
No supernova was detected following GRB 250702B. However, the scientific team is confident this is a non-detection, not a contradiction of the model.
Okay, so why the confidence? Why isn't this a deal breaker?
We circle right back to the JWST data. The extreme distance, 8 billion light years, combined with that extreme amount of obscuring dust in the host galaxy, that AV of 11 magnitudes, it acts like the ultimate celestial blanket.
It's just too far and too dusty to see it.
Exactly. That much dust would have easily masked even a relatively luminous supernova explosion. The non-detection doesn't rule out the existence of a supernova. It only rules out the very most luminous possible events. Given the data constraints, the physical impossibility of detecting that optical signal is by far the most likely explanation.
So we didn't see the predicted outcome, but the observational constraints, the distance and the dust, perfectly explain why we missed it, leaving the celestial consumption model intact.
That is the final analysis. The old models failed because they only considered the fuel available inside a single spinning star. The only viable path forward was to invoke orbital angular momentum, forcing us to recognize that the cosmos has these new, violent mechanisms for pairing a black hole with a long-lasting fuel source.
GRB 250702B teaches us that a black hole consuming its companion star in a tight, violent dance can power an ultra-relativistic jet far, far longer than we ever previously conceived.
So this deep dive into GRB 250702B has revealed a truly new class of cosmic explosion.
Solved through an incredible coalition of satellites, from the high-energy triggers of Fermi all the way to the infrared dust-piercing clarity of JWST.
We unpacked the two great contradictions, the duration of days versus the engine speed of half a second.
And found the solution in a new type of binary merger, A new way for the universe to be violent.
And every time we get data this precise, it doesn't just solve one mystery, it opens a dozen more.
Which leads us to our final provocative thought for you to mull over. We see GRBs almost daily. But this one was only solved because scientists were forced to track it continuously for days.
Right.
So if the Einstein probe detected that quiet X-ray precursor signal starting a full day before the main furious gamma-ray burst even began, how many other ultra-long repeating cosmic explosions have already occurred throughout the universe that we simply missed?
That precursor signal fundamentally challenges our observational bias. It's a huge deal.
How so?
For decades, we have been building observatories that are designed to catch the instantaneous flash and then move on. That's been the whole model. But if the onset of these day-long catastrophes is a quiet, gentle X-ray whisper that lasts for hours before the gamma-ray scream even begins,
Then we have likely been misclassifying or just completely ignoring a massive population of these ultra-long events.
exactly. GRB 250702B suggests that we may have to fundamentally redesign our high-energy observatories, equipping them not just to detect the initial burst, but to commit to tracking a single outburst for days, perhaps even weeks on end.
We might only be seeing the very tip of the ultra-long GRB iceberg.